Welcome to the Code with Jason meetup. Tonight we're going to do some genetic programming. We've done this once before in a Code with Jason meetup a pretty long time ago. I'm going to share my screen and show you what I've been working on, and then I'll describe what I want to do next. Share screen. Okay. So here is the program that I've been working on. You guys see a bunch of dots and stuff, right?
Yes.
Yeah. So these are my little critters. Um, they reproduce and evolve, but the problem is they never get any smarter. So the deal with these things is that they have vision, they can see east, west, north, and south. Um, and they have rules that say like if I see something green to my north, go north. Or if I see something green to the west, go west. But their rules are random. So it may be that they get a rule that says if I see something green to my north, go east, which is obviously not smart. When they hit one of these green dots, they eat it. The green dots are food. When they eat a
Mhm.
green dot, they gain health and it costs them health to move. So if you can keep eating, then you can keep moving and you can live a long time. But if you're not smart enough to find food, you're going to die. But the problem, these creatures never get any smarter. They kind of reach a local maximum, it seems like. See, the record high fitness is 15. That means they ate 15 pieces of food. But the other night, I let this run overnight. I let it run for like 85,000 generations, and the fitness never went up above like what it is now. And so there's something I don't understand. And I've spent a long time tweaking various settings and stuff like that. And none of those things have done the trick. So the conclusion I've come to is that I just don't know what the hell I'm doing. And I need to make the problem simpler. I need to make it sufficiently simple that I can understand what I'm doing and that I can design a system that evolves increasingly smarter creatures. And then I can ratchet up the complexity and come back to something like what this is now, but actually have it work. So I'm going to start mostly over from scratch. I'm going to use a couple of things from this program, maybe, but I'm going to start mostly from scratch. And unlike what I did for this program, because I allowed myself to be undisciplined, I'm going to write tests for most of the stuff. So I'm going to stop this program and I'm going to create a new one. Hey, Jonathan.
Hey, how's it going?
Pretty good. How about you?
Doing all right.
You just missed something critically important, so I'll show it again. This is my world of creatures that run around and eat green dots. Long story short, it's a genetic program, a genetic algorithm that does not work. These creatures don't get smarter over time. And so I'm going to build a new, simpler program and teach myself genetic programming better. Okay, whoops, I did not mean to stop sharing my screen. I meant to stop this program. Okay. So I'm going to make a folder for this project called Simple Creatures. I just came up with that just now. Okay. So let's decide an objective. I'm going to go back once again to this other project and run it because this will help us come up with an objective. So here's what I think I want. I think I want a world with just one creature and one dot. And I want the creature to like move across the screen. And when it sees the dot, okay, it's like this. Let's come up with like a prediction. Like, if I were successful in creating a world that evolved increasingly smart creatures, and the environment is just emptiness and one single green dot, and I let the creature move across the screen, if it gets smarter, what it should do is it should move until it sees the dot and then move straight toward the dot and eat it. That's the prediction that I would make. And so if I build something like that and my prediction is borne out, then I guess I was successful. However, and I'm curious you guys' opinion on this. That seems like so simplistic that it might not achieve much.
What would be some ways you could see this failing?
Yeah, good question. Obviously one way that could fail is like if the creature just keeps moving past the green dot and never moves toward it. Another way is like I can conceive of a scenario where the creature moves across the screen, sees the green dot, then for example goes south for one square and then continues going east. Like the rule is the rule is not sufficient to get it all the way to the dot.
So my understanding of the of genetic algorithms is that you have some sort of fitness function that
Mm-hmm.
basically scores how well you did. Um, and I mean, the easiest thing that I can think of is the scoring of how many dots you ate.
Yeah. Yeah, and Nelson, I feel like so that's consistent with what I was thinking about before. And even something we could maybe add to that is like the ratio of dots you ate to how much movement it took you to eat that many dots. Because it's like an organism that goes straight to the dot is fitter than an organism that gets to the dot in a circuitous manner.
Yeah, I agree with that.
Mm-hmm.
But that seems like it would be more complex, and maybe we should start with the simplest thing first.
I think I agree. So I think we probably want more than one dot because if there's only one dot, then the fitness function is like either you're completely fit or not fit at all. And it seems like that's too coarse. Does that seem right? Um, does anybody have an opinion about that? Because like if there's one dot and one dot only, then you eat the dot and you've achieved the maximum health that you possibly could ever achieve. And nobody's ever going to evolve to get smarter than that. Whereas if we have like three dots, for example, then you eat one dot, great, but it's not until you eat, you can be fitter than that and you can eat two dots and you can get smarter over time rather than just hitting that wall once you get to the one dot.
Doesn't that assume knowledge of the complete system for each organism?
Well, it does. Um, but to be clear, I'm imagining a pretty small world, like a fraction of the size of this one. Um, and sufficiently small that it wouldn't be a big deal for the organism to explore the entire world. Does that address that for you, Nelson?
Yeah, I think so. I'm a novice at this,
Me
so
too.
I'm it's a good I don't have the tools to be able to critique it further.
Okay, well, let's explore this together. First, I'm just gonna tweak this program a little bit. Um, I'm gonna do something that might be interesting. Instead of having 800 food cells, which is what I have now, I'm gonna have just one. I'm curious what that looks like. Yeah, the food cell gets eaten really fast. Okay. And instead of having a whole bunch of organisms, I'm gonna have just one. I think this might break my program though. Yeah, because the like reproduction threshold is just one organism, meaning when it gets down to just one organism in the population, it'll reproduce. So I'm going to set it to 2. Reproduction threshold is 1. Let's see what happens. Okay. So they die pretty fast, probably because nobody's ever eating anything. And I know I'm going so fast. I'm going too fast for anybody to see any actual code. Um, but I'm not expecting people to be following this part. Um, okay, so I'm starting them with more health so that hopefully they live longer. Okay, yeah, they're living a little bit longer. Now I'm gonna make the world smaller. Let's make it just like 10 by 10. Okay, that should give us a 10 by 10 square. That's not at all what it gave us. Okay, I made a mistake somehow. Okay. Oh, I just want to say screen height in cells equals screen width in cells. Okay. Okay, that's actually really small, even smaller than I was imagining. So we'll make it like 50. Okay, I think this is about what I had in mind. And I'm gonna do a couple things. I'm gonna make it so it slows down so we can see it better. Yeah, now we can kind of see what's happening. Um, I forgot what the other thing I was gonna do was. It doesn't need to be quite that slow. Okay. Now I'm just gonna sit here and think for a second. So the reason I did this is to help myself imagine what I'm shooting for. Um, I want to start with a fresh program, and instead of having this dot dance around, I want to have it be in just like one spot. Actually, I can do this. And I think I said, I wanted like 3 cells. Yeah, there we have 3 cells. But I don't want them to keep moving. Hmm. By the way, this can be somewhat mesmerizing to watch. I confess that sometimes I've sat here for like 20 or 30 minutes just watching these things. It's not very productive. Okay. Yeah, so I want to start the dots always in the same spot, and I want the organisms to start in the same spot also. Or I should say organism, because I only want one at a time for simplicity. Hmm. Yeah. Okay. You know, if I want them at fixed spots, whoops, I can just say like, oh, let's see. Okay, so X and Y, let's put one at 10, 10. Let's just start with that. Let's see where that puts it. Okay, there's a food cell at 10, 10. Let's put another one at 20 and 11. Let's see where that ends up. Okay, for some reason I want to scooch it just a little bit down. 20 and 14. And the next one I will put at 20 and 34. I'll actually put it at a slightly different spot. Whoops. I want to put it further to the right. Okay. Okay.
Sorry, would 0, 0 be top left?
Yeah. If I'm not mistaken. Okay. And now I want to start off my organisms each in the same spot. So let's do that. I don't know what determines the position of the organism. Oh, X, Y. Okay, so when an organism is initialized, it gets an X and a Y. Okay. Oh, and maybe generation initializes organisms. Yeah, there we go. Okay, and it gets a random X and random Y. So instead, let's do 0, 0. Okay. Okay. So now this is more similar to what I'm envisioning. Huh, and this is even interesting to watch. I actually can't tell what's happening because I thought there was going to be 2 organisms per generation, but I only see 1, or maybe there's 2 that are perfectly overlapping, although that seems unlikely. Okay, now I see 2. Okay, this purple one is like eating that piece of food. Look, our record high fitness is 1, according to that label at the bottom there. But then maybe it can't even eat enough to gain enough health to get to the second one. So let's give it more of something. Let's give it a starting health of 100 and a max health of 10,000. I don't know. Okay. So these organisms so far are not very smart. And I guess it takes it a long time to use up 100 worth of health. So maybe that's too much to give it. By the way, I'm going to split this screen to make it a little quicker. Okay. So where was that? Generation? No, organism. Okay. Let's say my starting health is 20. Okay. And I don't know what's happening now. I don't see anything on the screen. Okay, now I see some. Okay. So this guy must be starting by going straight up because the screen will wrap. So he goes up and then wraps around the bottom. And then he just dies before anything happens.
How much health do they lose for each movement?
Just one. So
they
I
get
guess it makes
two
sense.
when they eat something, and they lose one when they move one space.
Sorry, say that again.
They get 2 healths. So they're starting with 20. They get 2 for eating, and they lose 1 per movement.
It's slightly different. Their health actually gets multiplied by 2 for eating.
Okay. So if they eat it right away, they'd have 40. 20
Yeah,
times
before I
2.
changed the health just now to 100. So now obviously if they eat one, they go up to 200. And I did that because I wanted this might make sense or it might not, but I wanted them to get rewarded less for the earlier foods they ate because I didn't want them to get rewarded just for an accident of birth. You shouldn't be considered more fit just because you were lucky enough to be born near food.
Well, that's how the world works, Jason.
I know it is.
Get over it.
I was born like right next to this giant pile of bananas, and it just set me up for life. Okay. So now the behavior we're seeing is just this like one organism going across the screen over and over. And I'm not sure what to make of that. One problem is that I can't tell what's happening. I think what's happening, okay, every time a new 0 is output here, that's a new generation. So we must just be seeing generation after generation without much mutation. So I'm going to increase the mutation rate. And you know what? I'm going to increase, before I do that, I'm going to increase the generation size. Let's have 10 organisms per generation, because why not?
Okay, so what if, because it's like you're starting it in the same spot, it goes across, it doesn't get food, and it dies, right?
Mhm.
So what if the second generation moves down a notch and goes across the screen? It doesn't get food and it dies. The third generation moves down another notch, and that one hits food, and then it keeps repeating because it's learned it is now smart.
Okay. Speaking of smart, I am not smart enough to follow all of that. So can you run that by me again?
So currently you're starting at so say you start a generation in the same fixed position, right?
Mhm.
Goes across the screen, it does not find food, so it dies.
Mhm.
But the second generation, another generation is spawned 5 pixels lower, however you're measuring the
Mhm.
columns or the rows,
Mhm.
and it goes across the screen, it does not find food, it dies. The third generation is another 5 pixels lower, it goes across the screen, it finds food. So now it knows food is there, and then it gets the points.
Yeah. I see what you're saying now, but I think that would no longer be a genetic algorithm because because I want the behavior of the organism to be determined only by the organism's genome. In other words, it's like DNA. And if I do that, then I'll be like, I don't know. It's like I'm picking it up and putting it closer to food. I'm creating an accident of birth for it.
Hmm.
Now, the interesting thing here is that these organisms do seem to be getting smarter. Like they got smart enough to where somebody eats all three of the foods every time. But a problem is that there are so many organisms on the screen that I can't tell what's going on. And so, oh, what if we had a situation? Hang on a second. What if we had a situation where there were 4 concurrent worlds, for example, and each world has an organism, and each world is able to play out concurrently, and the fact that they're like 4 separate worlds would mean that we'd be able to easily watch what's going on in each world, but the organisms would still be able to compete. Because the problem now is like, how can I be sure that these pieces of food aren't getting eaten by like 3 different organisms or 2 different organisms or whatever, you know? Okay.
Does the same genetics have the same color at each generation?
Yes, 2 organisms with the same genome will be the same color. The trouble is your genome develops as you gain experience because the rules are like randomly assigned on the fly. Like for each new situation you encounter, you create a rule in that moment for that new situation. And so if you've seen a bunch of different situations and you turn a different color, you'll pass that same color on to your offspring. But I think what we're seeing with these organisms is that they are gaining new experiences as they're moving. And so they're coming up with new rules and their colors change and it makes it hard to follow them.
How so I'm assuming that there are 2 parents that give one offspring their genes, or is that wrong? How is the genetics modified then?
Ecosystem. According to the current settings, it's just one organism that reproduces exact copies of itself. It doesn't mate with another organism or anything like that.
So how do its genes change?
Mutation.
Oh, so it's just random mutation.
Yeah. Okay, and I changed the settings so that each generation only has 4 organisms in an attempt to make everything easier to follow. Oh, and I see, even though all 3 pieces of food are getting eaten, we can see that the record high fitness is only 2. And so that means one organism is eating 2 of the dots and another one is eating the 3rd dot.
Do we need more dots?
More food dots?
Yes, more food.
It seems like it might be helpful, huh? Let's add a couple. Okay, somebody's saying something in chat. More dots than dots. More dot. Huh. I can't even read it. It has something to do with World of Warcraft. Ah. I'm just going to focus on my dots. Okay, now we have, thought it was 6 dots. 1, 2, 3, 4, 5. Did I put one of my dots in an impossible location? Oh, how big did I make this thing? 50. Yeah, I put it off screen. Okay, so instead, I'm going to put this at like 27 and not 74 because that's not possible. 44. Okay, 1, 2, 3, 4, 5, and I saw a 6th one. Okay, so the record high fitness so far is 2. Let's see if these dots get smarter over time. Another challenge, and this goes back to the concurrent worlds idea. A challenge is that sometimes an organism's brethren will gobble up available dots before it can. And so it won't get a chance. I can't tell if, well, it at least has gotten smart enough to, hello child. It at least has gotten smart enough to eat 1 dot. 2 dots rather. Ooh, interesting. Okay, so more stuff is happening. So that one eats a dot, eats another dot. Oh, I thought I saw some more dot eating happening. Oh yeah, somebody ate that dot. But still the record high fitness is just 2. Oh, and now it seems like I was gonna say it got dumber, but maybe not. Okay, I am going to tweak some other things. Just out of sheer curiosity, what happens if we put the generation size back at 10? Does anything interesting happen? Because the bigger the generation size, the more chances we have to try out more genomes. And so, under certain circumstances, the faster evolution would occur. But again, there's the problem that the more individuals there are, the faster the dots get eaten, and no one individual has a chance to eat very many dots. And so I think I've created versions of this program where the dots will just, the organisms will just gobble up the food dots like piranhas, but they don't need to be very smart in order to do that. And so they can eat all the food even without being very smart. And so then they never evolve to get any smarter because they don't need to be.
So there's a few levers that we've pulled so far. We can change the size of the world, we can change the amount of food, the location of the food, the number of agents traveling through the world. Can we change anything else, like what pathfinding algorithms are available, or anything about how the agent senses the world, like if it, how far ahead of it it can see, or if it can sense other agents in the world? Can we do any of that?
some of that stuff. Sorry, Carl says, is the output integer the current round score or the record high? It's the record high. Oh yeah, current round. Oh, okay, I see what you're asking, Carl. This number in the very lower right is the record high, and then each one of these things is just output to the terminal. That's like the record high at the time. Okay, and Nelson, to address your question, we can change the algorithm that's available. And I'm gonna tweak a few things here. So I changed the generation size back to 1. I'm gonna make it so it doesn't slow itself down as much. Okay, sorry, Carl, I'll get back to that in a second. Oh yeah, I forgot that I can't have just one organism. I think I want to modify the program so I can. Okay, Carl says, can we modify the terminal output to show that round score as well as the record high? Right now we could be hitting the record high early, but not in subsequent rounds. Oh, we actually do have that, Carl. I'll change this back to something. You can't see the words because I made the world too small, but the number to the right is the record high fitness, and then this other, what's currently a 0, it's the fitness score of the fittest individual for the most recent generation. Okay. So my generation size is 4. Sorry, I'm feeling a little bit mentally scattered and I want to get myself straightened out because I don't want to confuse myself or you guys. Okay, so I set the generation size to 2. And this thing is just going across the top and it's never moving. And when we had a bunch of individuals, it seemed like evolution was occurring. And they get smart enough to eat the dots. But when there's just like one, when the generation size is just 2, they don't get smart enough to eat the dots. Or
Well,
apparently,
we're agents, we're increasing the chances, right? Like, uh, with just 2 in the world versus 4, with 4, you have double the chances of getting a smart agent.
right. Yeah. So the trade-off is like the more organisms you have, the more genomes you get to try. And so the faster you find a successful genome. But the negative of that is the more organisms we have, the more the organisms will interfere with each other. And that interference is a real problem. And so I think the question I want to ask myself is there a way that I can have a very small number of organisms, like 2, preferably actually 1, or maybe 2, I don't know. Is there a way I can have these small number of organisms, but still have evolution advance reasonably quickly? And I think maybe the answer to that is I want to increase the mutation rate or increase the number of concurrent worlds or both. I think increasing the number of concurrent worlds is something that that would be too much work to do right now. But Nelson, to get back to something you said, can we change the available algorithm? Yes, we can, and that might actually be something interesting to do. Let's go to the genome class. So here, Nelson, we have these possible directions from which it selects. You can go up, down, left, right, or the same direction. And something I've done before that I'll do again is I'll limit the possibilities to just up and down. And for some reason I have those duplicated here, so I'll address it here also. So up and down, that's not what I meant to keep. I meant to keep like up and right. Because if you can only go up and down, then obviously you're not going to get left and right. Okay, you can go up and right, and that's all. Okay. And my thought with this, the reason I had done this earlier is because I thought maybe if the algorithm is more constrained and the possible behavior is simpler, then it's like a coarser resolution. And so the spectrum of possibilities is narrower. And because the spectrum of possibilities is narrower and there's fewer options to choose among, you'll hit the successful one more quickly. That was my thinking. I don't know if that's right or wrong, but we're having that thing again where it just goes across the top. I'm going to do a couple things. I'm going to make it so when you mutate, more of your genes get mutated. I'm going to make it so the mutation rate is higher. Let's see if that has any observable effect. Okay, so I see the record high fitness is already 4. That seems kind of high, given that the total number of dots is just 6. I'm going to rerun that and see what happens. Okay, record high fitness is 1 right now. And I'm not seeing any changes in behavior. I'm going to add some output so we can tell when the organisms are mutating. Yeah. Mutating. Well, I guess it only mutates 1 in every 100 organisms. So, no, 1 in 10 organisms. Okay. All right, so mutation is happening at a pretty decent rate, I guess. The record high fitness is 1. We've had 4 mutations so far. Oh, wow, now it's up to 4. Okay. Huh, so it eats 4, and then the generation dies, which seems surprising. Because, like, if it eats 4, then you're going to be really healthy. Oh, but maybe it's like brother died. Because maybe the one organism is smart, but the other one is not. And if your brother dies, even while you're still really healthy, you're not going to get a chance to you're not going to get a chance to continue to learn. So we have to make it so regeneration happens not when one of the two organisms dies. You know, and another way to put it, that the population starts at 2. We don't want to create a new generation when the population goes down to 1. We want to create a new generation once everybody dies. Okay, so let's do that. So we have a reproduction threshold. Wait, can we just set the reproduction threshold to 0? Maybe that does what we want. But then there's nobody to reproduce. Okay. Is population at population threshold? Okay. So if we get down to the, oh, and here it kills the unhealthy organisms. Okay. If we get down to the population threshold, then it creates a new generation. We want to hang on to like the last survivor. So when it takes the fittest organism, that's the fittest of all the living organisms. Can we do all the... How do we keep track of the last survivor? Okay, so here we're killing any unhealthy organisms.
If we know all their healths, can we can we keep the one with the highest health?
Yeah. What if each time we just kill the single unhealthiest organism?
Yeah, that works too.
Kill... Wait, do we want to kill the one that has the least health or the least fitness? So fitness is how many pieces of food you've eaten, and your health is basically how many pieces of food you've eaten minus how much you've moved. I'm not even sure why those are two separate things. Anyway, I'm going to say kill least healthy organism. Okay, and that's an ecosystem. Okay. Now, I'm actually going to do this. Let's go to ChatGPT. Say, change this to kill least healthy organism and update the behavior. Change this method. Okay. Okay, self.org. Oh, weird. Didn't know you could do that. Okay, but I'll try that and see if it works. Yeah, it did not work. Oh. What was the argument that organisms? Okay. Why did it take an organisms argument? Whoops, I didn't mean to undo that much. Self.organisms.copy. I think that was just like, there was no good reason for that. Oh yeah, ecosystem.kill least healthy organism, ecosystem.organisms. That makes no sense because the ecosystem already knows about its own organisms. Okay, let's see how this goes. Index out of range. Okay, maybe ChatGPT was onto something when it said this. Oh, organisms ordered by fitness. Okay, fittest organism. Yeah, I think we don't want to use fittest organism anyway. We want to say when we're down to one organism, we want to Oh, maybe we can do this. We can say healthiest organism equals ecosystem dot healthiest organism. And then max fitness of last generation equals ecosystem dot, oh, we can, okay, max fitness of last generation equals healthiest organism dot fitness. Okay. And then when we create a new generation, what we'll be reproducing with is the healthiest organism. Okay. And now we just have to make a healthiest organism method. Now create a healthiest organism method. Okay, this is like a not smart and reckless way to code. So like if this works, we'll just be lucky. Okay. It moves very little and it's just constantly creating a bazillion new generations. All right. So I can't be too surprised that it doesn't work because like I said, this is a really reckless way to code. We're just kind of doing stuff. And so we might finally have to start over and be more careful. But I'm going to make a quick attempt to salvage this before I give up and say that. Okay. So it's like death is everybody just dies right after they're born. and I don't know what's going on. So I'm just going to undo back to where we were.
So when I get stuck,
Mm-hmm.
I either do one of two things: either go back and read the documentation, or
Mm-hmm.
find some code that does something in the genre that I want, that
Mm-hmm.
that I can take as an example. I don't know if things like that exist, like example genetic algorithms for this type of thing.
Well, I have a saying, when all else fails, do it the right way. Um, and so I've kind of been shooting from the hip with this. Um, and if you shoot from the hip for long enough, you eventually create a big enough mess that it collapses under the weight of its own complexity, and you get confused and you can no longer easily make changes. And that's the point at which I arrived. And so if I had like a nice complete test suite for this program, that change I had wanted to make a minute ago would have been much easier to make. But since I don't, it wasn't. And I confused myself and my change didn't work. So I think what I want to do, and we'll have to do this next time because we're about out of time for today, is I'll have to start over, but more carefully and with tests and all that. Okay, there's something in the chat here. There's always a least healthy, even if they're all at max health. Yes, that's true. Travis needs to head out. See you later, Travis. Thanks for joining us. Okay. Well, I think that's a decent place to call it a day. We didn't get anything super interesting, but at least I think we learned a few things about the behavior of our program and all that stuff. So thanks everybody for joining me, and I will see you next time.
Take care, everyone.